Next type of graph, absolute value graphs. We've talked about the very basic absolute value graph of linear functions, but what about absolute values of other things? So the first one to think of, y equals the absolute value of some function. What will happen in the graph here? We will end up with, well, this is a bit misleading what I've said, symmetry in the x-axis. The actual picture is not symmetric, but what I mean by that is whatever's below the axis now reflects above the axis. So it's sort of like the axis has become a mirror, and that's why I use the word symmetry. So there's good old random graph. If we want to do absolute value of random graph, it's basically whatever's below, see you later, it's gone, and reflects above. So anything below reflects above. That's absolute value function x. As opposed to function absolute value of x, symmetry in the y-axis, and in this case that is accurate. It will end up being symmetric in the y-axis, because you're going to end up with an even function if you think about it. Because when you substitute in negative x, you're going to go absolute value of negative x, which is x, you'll get the same as function x. So what does this mean? It means whatever's on the left-hand side will disappear, but whatever's on the right-hand side will reflect over. So it will be function absolute value of x. What about if it's absolute value of y is equal to function x? Well, again, we're going to have some sort of symmetry involved in the x-axis here. This time, watch this carefully, reflect the part of the function where the function is greater than 0 in the x-axis. What does that mean? Okay, here's our picture. Below, again, will disappear. Absolute value of y equals function x, you could think of as y equals function x or minus y equals function x. So here's what ends up happening. We get rid of what's below and we reflect what is above now goes below, because the y values are going to be the same now. Remember the other ones, the x values effectively were the same. Well, this time, because it's on absolute value of y, the y values are staying the same even though it's negative, so it reflects in the x-axis. So absolute value of y equals function x. What about if we had absolute value of y equals function absolute value of x? Now we're going to have symmetry in both of the axes. Here we'll reflect the part of function x that's in the first quadrant into all 4 quadrants. Because now we've got absolute value of x, so as far as we're concerned, we're only putting in positive numbers. But we've also got absolute value of y, so the answer is only going to be positive numbers. So this one, see you later, we're just left with the first quadrant, but it goes into all 4 quadrants. So absolute value of y is equal to function absolute value of x. Another way of thinking about that is you could do y equals function absolute value of x first, and then do absolute value of y of that new function. You'd end up with the same picture. Y is equal to the absolute value of function absolute value x. This is going to have symmetry in the y-axis, but reflection in the x-axis. And there's the description of what's going to happen. Reflect the part of function x where x is greater than 0 in the y-axis, and then reflect the result in the y-axis. Here's random curve. It's probably easier to think of it this way. That would be y equals function absolute value of x. We've already worked that one out. But now I want y equals the absolute value of this one, so whatever's below reflects above. We end up with that one. Oh, let's keep going. Absolute value of y is equal to the absolute value of function x. Now we'll have symmetry in the x-axis and reflection in the x-axis as well. There's our instructions of what happens. Okay, y equals function x. That would have been y equals the absolute value of function x. We did that one already. But we now want the absolute value of y equals the absolute value of function x. Oh, look at that one. That's a beauty. Yeah, okay, I think I stopped there. That's probably way beyond what we'll actually ever get asked, but you know, it's fun. Let's have a look at square root graphs. We have to draw the graph of the square root of a function. Again, you start by drawing your graph, whatever it happens to be, and these things. Well, we know that the square root of function x is only defined if the function is positive. But we also know, because we're talking positive square root here, the answer will always be positive as well. So what do I start off with? There's random graph. First thing I do is simply rub out anything that's below the x-axis, because you can't find the square root of the negative numbers. So those x values are no longer in the domain. They've gone. Stationary points will still be stationary points. Yes, the y value might have changed, but same x value. So all right, we have a stationary point up there. It's a number that's bigger than 1. If I find the square root of a number bigger than 1, it gets smaller. It'll still be bigger than 1, of course, but it'll get smaller. So I'll just lower it down a bit there. We don't seem to have any other stationary points. Okay. Horizontal and oblique asymptotes may change. So similar to the square one that we saw yesterday, we'll find the square root of our asymptotes now. So that one is less than 1. Find the square root of a number less than 1, it becomes bigger. So it'll go up a bit. It'll still be less than 1. So I'll put it about there. Again, if we had an oblique asymptote that say y equals x, the new asymptote would be y equals the square root of x. So parabola on its side, it would go towards that. The square root of function x, so the new graph will be less than or below the old graph if the function is greater than 1. Okay? Find the square root of a number greater than 1, it gets smaller. The new graph will be bigger than the old graph if function x is less than 1. Find the square root of a number less than 1, it gets, well, it's bigger. It's still less than 1, but it's a bigger number. All right, so 1 again becomes a really important point because the square root of 1 is 1. So let's plot those in. We know the curve's going to stay at those values. Now, x-intercepts. This is where we really have to be careful. Let me show you something which you may or may not have ever realised. I'm going to talk about the function y equals x to the power of a on b. There's x to the third, so 1/3. There's x to the power of 2/3. So what do we notice? If a over b is less than 1, in both of these cases they're less than 1. The curve is concave down in the first quadrant. So it's always concave down in the first quadrant. That will always be true. You end up with a vertical tangent at the intercept. The left one is quite obvious. The second one maybe not as obvious, but again it would be a vertical tangent at that point. Then you get to 3 on 3. Well, that's x to the power of 1. We've now got a straight line. Okay, it now gets bigger. So 4 on 3, 5 on 3, and 6 on 3. Have a look at the first quadrant now. It's changed to concave up. So as soon as that power gets over 1, the curve will become concave up. And we now have a horizontal tangent at the intercept rather than a vertical tangent. Let's say it's possibly something you never even realised before, but that will always be true. Have a look at these then. So my original graph was x to the power of 4. If I'm going to draw the square root of that graph, then I must get x squared. So I know that the x-intercept will become a little bit less flat. So remember, as the powers go up, it gets flatter and so on. So I know it'll look like that. Now, if I wanted to draw y squared equals function x, all that happens is we reflect what's above is below, because y squared equals function x is the same as saying plus or minus square root. X cubed. Okay, concave up in the first quadrant, but have a look at what happens when you find the square root, because you can't find the square root of a negative number. In this case, what's below disappears. This becomes 3 over 2 is the power. Well, 3 over 2 is bigger than 1. So it's concave up with a horizontal tangent. And if it was y squared, again, we'd reflect below. So if we were starting with, say, a double root, y equals x squared, now y equals the square root becomes y equals x. You're now going to get a V shape, like the absolute value curve, if you like, because it's a linear function now. So it's coming in sharp because it's coming from both directions. So it's not a turning point. That's one of the biggest mistakes people make with these ones, is they'll have a turning point on this when it should be a V, a nice sharp point. And then you get a cross on that one for y squared's function x. Okay, our starting one was 5 on 3. So our new one, if you find the square root of 5 on 3, it will become 5 on 6, which is now less than 1 in the power. So you'll notice the curve changed to being concave down It was originally concave up. And then the last one I've got there, 4/3. Well, find the square root of 4/3, we'll get 2/3. Again, it's now less than 1, the power changed from concave up to concave down. Instead of a horizontal tangent, it's now got a vertical tangent. And again, that's a nice sharp point there. It's what's called a cusp. Okay, that's what we call a cusp. All right, back to random curve then. All three of these look to me like they're single roots. They're coming in sharp. So if I find the square roots, it's going to look like a square root graph, which is a bit like a parabola on its side. But what I do know is that power is going to be less than 1. So it will be concave down and it will have a vertical tangent at that point. So there are those x-intercepts. I will attempt to draw. Well, I might have exaggerated the vertical tangent there a bit, but there's meant to be a vertical tangent at the side. So yeah, real dodgy there. It should probably be symmetric, but anyway. But I guess the point I was trying to make is, yeah, this comes to a nice vertical tangent, a bit like a semicircle, if you like. There's going to be a vertical tangent there. So there's y equals the square root of function x. Of course, if they did ask us to draw y squared equals function x, all we have to do is reflect it. And then we get our new graph, y squared equals function x. Okay, bye.